Going through this, you know, I would say unusual start to the semester, the tragic events from December, they're still, you know, weighing on us heavily, and our thoughts remain with those who are most deeply affected. You'll notice that, you know, the place has changed and the time has changed. And also with that, the capacity of the room has changed compared to the usual one. These adjustments reflect realities and limitations that we've had, you know, as a community to organize these sort of events. And so we appreciate your flexibility and your understanding as we navigate this together as a department. I also recognize that this specific timing may collide and overlap with you know, some of our colleagues' teaching with you know, duties and departmental requirements. So please know that the decision that we made as a colloquium committee was made in good faith and with the best intentions to keep this series running at a time where we would hope that you know most of our community could you know reasonably attend and would not have to walk across half of the campus. Which may have increased the barrier for people to attend these sort of events. And so, despite the challenges, I would say it means actually a great deal to me to see so many of you here. I think your presence affirms the spirit and the resilience of this department. We have a full and exciting colloquium series coming up this semester, and I hope that these gatherings continue to, you know, offer a sense of continuity, reflection, and shared purpose as we move forward together. With this being said, John, please introduce the speaker.
All right, well, thank you, Matthias, and thank you all for coming. It's my pleasure to have Professor James Aguirre from the University of Pennsylvania here to give a colloquium today. So James was an undergraduate at Georgia Tech, did a PhD at the University of Chicago working on C&B experiments, was an NRAO Jansky Fellow at Boulder before moving on to Penn, where he is now and coming to visit us from. So I think I've been working with James for probably as long as I've been working with anybody. So it's great to have you here, and take it away. We'll get the lights for you.
So I really want to say I appreciate the invitation. It has been a real pleasure to be able to come up here and have a delightful visit so far. It's the first time I've been here, actually, I guess. But like I said, I'm really glad to be here. So I'm going to be talking about measuring the optical depth to recombination. And when I wrote the title and abstract here, I said why it matters. And I do sometimes feel a little annoyed when I read proposals and scientific talks. Oh, there's an urgent need to do this, or this is, you know, crucial. And I think we all understand that there are things that really matter and there are things that are really urgent. And we have the privilege of spending time with things that give us maybe a little more perspective on the universe, but we have this great privilege to think of things that matter in a scientific sense. So I do want to try to explain how that works. And I'm going to go through, I'm trying to cover a lot of ground, and that may mean I have to skip some things a little bit more quickly than I would like. Because I'm going to talk a little bit about cosmology, a little bit about instrumentation, a little bit about particle physics, and various things to try to fit this story together. So I'm going to have to worry you the first here about sort of just a brief history of the universe and some key events in it so that we are all sort of speaking the same language about what we're trying to do. And then I'll introduce this optical depth quantity, which I'll often refer to as tau, and try to explain why we would want to care about measuring it. And then I'm going to have to talk a little bit about the actual measurements that we're going to do with the measurements of neutral hydrogen. I'm going to have to talk a little bit about both the theory and the experimental setup of how this is done to give you some idea of how we might be able to do it. I'm going to talk in particular about an experiment that I've worked on now for many years. And of course, time permitting, I'll try to get some sense of where we're going with this. Okay, so a brief history of the universe. As a cosmologist from Penn, we joke that we're sort of required as a condition of employment to show some history of the universe slide as the first slide in every talk. So I do want to do this one. Of course, one of the things that I want to point out is we think there was some event at the beginning here that goes by the name of the Big Bang. The details of it are not going to concern us too much here, except that the universe was hot and dense there, and it has been expanding ever since. And so some key things that we want to note are that when we observe light from coming from a long time ago, a great distance away, we're going to see that light being redshifted it will appear at a longer wavelength than it was when it was emitted. And so we can make use of that as an observational fact and to actually measure distances and times in our expanding universe. So that's one thing I want to point out. The other is that there's this extraordinary series of, maybe you would call them coincidences, that at about 400,000 years after this Big Bang event, the universe is cool enough that we get not a primordial soup of particles, but neutral hydrogen and helium, which is primarily all that exists at that time. And when that happens, the plasma that is is glowing at a temperature around 3,000 Kelvin, and it has imprinted in it a remarkable amount of information about the state of the universe, where the universe is more or less dense, whether it's spatially flat, and a number of other things that we've figured out how to extract from just the sort of fluctuations in the light emitted at that moment, 400,000 years after the Big Bang. Now, another kind of remarkable fact is that the universe becomes cool enough to be effectively electrically neutral, and that means that light can propagate freely. There's very little optical depth or obstruction to the light propagating for a while, and then an important thing happens that we're all here, that we can form stars. Those stars produce UV radiation, and that starts to ionize the hydrogen again and the helium later as well. So that produces now some sort of a screen of free electrons. And so if nothing else, light passing from the Big Bang to, or from the cosmic microwave background to us has to pass through this screen of free electrons. And fortunately for us, there's enough time delay in here, the universe expands enough, and that the universe is not opaque to the microwave background light. It is more or less transparent. The probability that a photon from the microwave background interacts via Thomson scattering with some free electron over the course of a 13.7 billion year travel time, measured from our point of view, is only a few percent. So in fact, we can actually see this microwave background light. The universe is more or less transparent to it. And measuring exactly how much it has scattered is going to be kind of the key thing we're going to do here. So we're looking back through lots and lots of stuff that's happened, and we're going to try to look back to the microwave background. So I just want to give a couple of key things. Now, a lot of what I'm saying here is informed speculation, informed theory about what happened. Some of these things are not really well observed. So we have direct observations of the microwave background. There is a period of time where we don't have good observational evidence of what's going on. There aren't any stars to illuminate things. And so we really don't know in detail what is happening. We do know that eventually gravitational collapse produces the first stars under some form. And we know that they must form black holes either directly, that's a little unclear, or via normal stellar evolution and collapse thereafter. And both the accretion onto the black holes and the production of a lot of stars then creates heavier elements, which creates further generations of stars. And by roughly 500 million years after the Bang, we have direct observational evidence of galaxies, things that we would call gravitationally bound collections of stars. And by around a billion years after the Bang, the light from those stars has produced enough UV radiation that any hydrogen atom that didn't find itself inside of a galaxy has now been ionized, which turns out to be the bulk of them. So most hydrogen we think that was ever formed back here in the Big Bang is in between the spacing galaxies in some ionized and diffuse form. And only a small fraction actually ends up in galaxies and stars and other places. Okay. So what is this quantity tau that I want to talk about here? So like I said, we're looking back, we're seeing light that is coming from the microwave background. It's been traveling for 13.7 billion years, and we see it through the screen of all the things it could have passed through. Now, there's lots of interesting things that it could have passed through. It is lensed gravitationally by the presence of mass in the universe. It might pass through a cluster of galaxies, and so it might experience some scattering from hot electrons in that cluster, and so you might see distortions in the spectrum of the microwave background in the cluster, or just shifts in the effective Doppler temperature of the microwave background. There is some possibility for complete absorption from various things, although that is relatively low. And then, of course, there's always the possibility that on its way it will encounter some free electron and scatter via Thomson scattering. So that's the thing that we're trying to get at here, is basically a relatively simple quantity. I'm going to integrate all of the free electron density. I'm parameterizing it as a function of redshift. So you can think about that as time back to the microwave background, or even as a distance. So the usual definition of optical depth would be integrating along some path, some way. And so I'm integrating along some distance back to the emitting surface here. So I need to know the free electron density. The average free electron density is a function of time in the universe. And then I'm going to multiply that quantity, which will have units of inverse area times the cross section, and I get a dimensionless quantity, which is the optical depth. And as you may know, if you spend a lot of time thinking about radial transfer, this isn't quite a probability, but for small values of tau, the optical depth is sort of like the probability that a photon will interact with, in this case, a free electron. And we think this number is around 5%, 0.05. So it is a relatively low probability that some CMB photon will, in the course of its long journey to us, actually interact with a free electron. Now, one thing that, of course, is true is that the light from the microwave background is distorted in some sense by this, and a couple of things are important. One is that you may recall that Thomson scattering is going to affect the overall amount of light that gets to us. Some of it goes in directions that we don't then observe. And it also can produce polarization. And so we can look at the polarization in the microwave background, how polarized is the effectively thermal light that should have been unpolarized on emission, how polarized does it become, and so we can look at that. And we can also look at how much the amplitude is. And it turns out this also will have some dependence on angular scale. So let me just show some boring plots here. Astronomers like to turn the wonders of the universe into incredibly dull plots. So here, what I'm plotting is, as a function of angular scale in the observed microwave background, we're calculating the polarized, a particular part of the polarized power spectrum. And the thing to notice here is that large scales, that is to say, things separated by large angle on the sky, are over here on the left, and small scales are here on the right. And you can see that as I change the optical depth, what happens over here at small scales is not unaffected, but it's relatively minor effect compared to what's happening on large scales. So on very large scales, the apparent polarization of the universe gets much more increased the larger the optical depth is. So one way to measure directly from looking at the microwave background itself, even though we can't see the undistorted thing, we can look at models and see what is happening on large scales compared to small scale, so we can directly measure it. Now this is hard. If you do astronomy, you'll know that measuring large scale is a difficult thing. We have something called the Milky Way, which tends to cover a large fraction of our sky, and it produces microwave emission, which is confusable with the thing we want to measure primordially. So this is not necessarily an easy thing to do, but in principle, with satellite or balloon mission, you can do this. From the ground, it's very difficult to measure large angular scales. The other thing you can do is you can look at this overall effect of suppressing the amount of light coming through from the microwave background. And so I think this plot doesn't quite capture it on first glance, so let me just walk through. So as I increase the optical depth, I move from black to red to blue. And you'll notice there's an overall shift downward. But the thing you should maybe harder to see is that shift is kind of less pronounced at the large scales and more pronounced at the small scales. So there's an overall sort of shift in the amplitude, but as a function of angular scale. And so in principle, this is also measurable, but just looking at the fluctuations in the brightness of the microwave background. There's a question.
A naive question. So if you're looking at, say, cosmic microwave background compared to, say, Milky Way radiation, shouldn't the cosmic microwave background stuff be redshifted so it's actually spectrally distinguishable? Like, why exactly does the Milky Way block it?
Right, so the question is, why is other emission light from the Milky Way confused? And it's an excellent point. One thing I don't show directly here, but is true, is this microwave background intrinsically has a very close to perfectly black body spectrum. Right, it is the best black body we've ever measured. And so in principle, looking at the spectral behavior of your light emission is very good at separating intrinsic microwave background from other things, but it is not perfect. And in particular, what is happening on large scales is that you have relatively few spatial modes that you can measure that you're trying to separate out what is spectrally going on at those large scales. And to the extent that they're correlated with other things, you can kind of try to pull it out, but there is still some sort of fundamental limitation to how well you can do that. Okay, and then the thing that, so this is just saying how would you measure it in the first place, but then the real reason why we care about this optical depth is, well, for one thing, if you've done model fitting, you know that anytime I have to fit for a parameter that I don't actually care about, and in some sense, this optical depth is not a fundamental cosmological parameter like the matter density or the baryon density or the scale of initial fluctuations or something like that. It's sort of a nuisance. It's another thing you have to marginalize out. But it also is degenerate with some other interesting things that you would like to measure. So one of the things that can be done with the microwave background as well is to look at the original light that we see in the temperature power spectrum and compare it to what we see after that light has passed through masses on its way to us. So we look at the lens version of the microwave background. And by comparing what happens at early times from the initial thing to the lens version, what you can ask is how much has the microwave background light been distorted as a function of angular scale, and that is sensitive to various kinds of mass between you and the surface of that scattering. One of those masses could be the neutrino. And importantly, the neutrinos do a sort of an interesting thing where because they are light, at early times they're going to be nearly relativistic and they're going to not contribute to clumping up, and so they're not going to affect the clumping of matter significantly. But as they start to cool, you'll start to see on on small angular scales, large L, that they start to affect the amplitude of the microwave background. So there is a small but in principle measurable effect of neutrino mass on the microwave background spectrum. Unfortunately, its effect looks an awful lot like this. And so if you can't figure out independently what your optical depth is, it's going to be somewhat dependent with, somewhat degenerate with the effect of neutrino mass. And I guess I'm not a particle physicist, so I don't want to get too far outside of my lane here. But I will point out that when we do care about measuring the sum of the neutrino masses here, this is what the cosmological measurement is sensitive to, for a couple of reasons. One is, of course, neutrino mass is strictly speaking beyond the standard model physics. We don't really know why neutrinos have mass. We don't know what the mechanism is. Maybe it's a hint of something more profound. But knowing what the absolute value of it is, rather than the splittings that we get from neutrino oscillation experiments, is a hard particle physics measurement. And so the hope is that cosmology can help weigh in on that. And if we knew actually what the sum was, that might also help distinguish the ordering of the masses and other things. So we can actually hope to do some real interesting fundamental physics if the cosmological measurement is good enough. Okay, so like I said, I'm not a neutrino physicist, so I won't try to motivate it more than that. I think, maybe we intrinsically want to know this. But in the way, there's this nuisance parameter. So let me just pick it apart a little bit so you can see how we might think about trying to actually measure it in a different way than the ones I've outlined so far. So if I pull apart, so one thing that you'll notice about this expression that I showed earlier, sigma Thomson is, of course, a fundamental physical constant. And this part of the integral here is stuff that depends basically only on cosmological parameters. So the h of z is the Hubble parameter. And a lot of this is going to depend on things like the baryon density and the matter density and so on are hidden. And it turns out that those are things that from various other experiments we think we know reasonably well. Not perfectly, but reasonably well. So in some sense, this expression can be sort of factored into bits that depend on cosmology that someone else has determined reasonably well, and measuring the average number density of electrons in the universe. And because most of the universe is hydrogen and helium, most of those electrons are going to come from either hydrogen or helium. And in particular, the bits that don't come from hydrogen but come from helium, we think come about in two steps. One is first ionization of helium is pretty close to hydrogen, so whatever ionizes hydrogen at a first pass is going to get that first electron off the helium. Second ionization of helium is 54 electron volts, if I remember correctly. It's quite high. You need some fairly energetic photons to do that, and we think that happens much later in the universe's history. than ionization of hydrogen, sorry. So we're going to kind of split off that part and say, we know it happens. Because it happens later, the electron density is lower, the universe has gotten bigger, and so it has less of an effect. So I'm really only going to focus on hydrogen, but bear in mind that I am aware other things exist. Beyond hydrogen and helium, we don't get a lot of free electrons coming from other heavy elements because they're not that abundant. So we're basically really interested in measuring the ionization fraction of hydrogen and its actual density in the universe. Oh, and I guess, sorry, I added the slide a bit late in the production, so it's perhaps a bit out of order, but just to make the point that if you look at sort of a current state-of-the-art microwave background experiment, they are claiming that they can measure the sum of the neutrino masses to some reasonably small error bar, about 15 millielectron volts in the best case. And they can also measure things about the optical depth with an error bar that is smaller than the current limits. And so I guess I should say I'll come back to this number. 0.007 is I'll compare it again because I don't expect everybody to remember it. But the point is that the claim is that this can be measured from the microwave background measurements only. But the neutrino mass measurement improves dramatically if you can decrease the error bar on tau. Okay, so how can we actually go about measuring neutral hydrogen directly? So I'm going to focus on one technique. Those in the know may know that there's more than one way to measure hydrogen in the early universe, but I'm going to focus on measuring fluctuations in the emission of hydrogen. And in particular, because I'm thinking about neutral hydrogen, we're going to look at the hyperfine splitting. So that's going to be the key thing. And whether or not we see that particular transition in emission or absorption is going to depend on the state of the gas and also radiation that's illuminating it. And then, of course, whether or not we see it at all is going to depend on whether the hydrogen is neutral or ionized. So in principle, if I looked at early in the universe, this is some simulation cube of a chunk of volume of the early universe at a few 100 million years after the Big Bang. We should expect to see some regions where there is neutral hydrogen that hasn't been ionized by stars, primarily stars, and I'll come back to that in a minute. And then there's some regions that have been ionized. And so we should sort of see some sort of Swiss cheese-like picture of the universe that in principle is discernible in 3 dimensions. I can look at 2 dimensions projected onto the sky and a 3rd dimension from the redshift of the hydrogen line emission. And okay, so here's an animation of what I'm trying to describe there. So again, a simulation cube where we're simulating the formation of galaxies and stars and UV radiation. And as time goes on, we're sort of rotating just to give you a 3-dimensional view. So time is progressing here as time went in the universe. We will see that there's sort of bubbles of ionized material forming around places where stars are forming. We happen to think that those are actually the densest places in the universe because that's where gravitational collapse takes over first and where I make stars first. So we think that what is going on is that the most dense places are going to ionize first, and then as time goes on, those ionization fronts spread out and more of the universe becomes ionized. So quantitatively, the way we're going to think about this is there's kind of 3 quantities that I'm going to care about, which is where is the hydrogen? So delta here is measuring how overdense is a region of the universe compared to the average in matter. The M is for matter. So where is the hydrogen? What fraction of it is ionized? And then there's this additional complication. Because I'm looking at this hyperfine transition, I care about the relative populations of the upper and lower states, which I'm going to characterize by this T-spin parameter. So basically, you can think about it as I heat up the gas, T-spin is going to go up. As I ionize the gas, the ionization fraction is going to go up. And as I pile more material into a given region of space, the density is going to go up. So the actual observable signal is some combination of what fraction of the material is ionized times how much of it is times whatever temperature it is. And strictly speaking, because this is radiation, we're measuring it against always the microwave background. So you notice that T-spin doesn't appear by itself, but it's with respect to the background temperature of the microwave background. So we can think about, the actual measurement of this is hard, people are trying, but we can think about making sort of an average measure of how much the hydrogen is emitting or absorbing relative to the microwave background, and plotting that versus, well, here you'll see redshift. So this is how much the universe has stretched out the light. This is time since the Big Bang. And then this also maps into observed frequency. So I'll point out we're looking at sort of 10 million to 1 billion years after the Big Bang. Those correspond to redshifts for redshifts of over 100 to down to about 5 or 6. And the observed frequency, because this particular transition happens at 1420 megahertz, 21 centimeter wavelength, and that will get redshifted down into the tens of megahertz to 100 megahertz. So we're thinking low frequency radio here. This is FM to not quite AM radio. So if I look at early times, low frequencies, then what I will see is that indeed hydrogen is in equilibrium with the microwave background. It turns out because of the expansion of the universe, the hydrogen becomes colder than the microwave background, and so we actually see it go into absorption here. There is a sort of strange effect here, which I won't get into in detail, but basically when the first stars form, they produce ultraviolet radiation, which you would think might heat up the gas, but because of an interesting atomic physics effect, it tends to depopulate the upper state here, and so effectively see the hydrogen go into absorption. And this point at which heating begins, we think, in the sort of standard picture, what has happened at this point is stars formed. Okay, so if I don't have direct collapse into black holes, in order to make a black hole, first I have to make a star, then I have to have it collapse to a black hole. That black hole can start accreting material, which tends to produce X-rays. The X-rays will travel great distances through the universe as compared to the UV photons, and they will start to actually warm the hydrogen gas. And so the sort of increase that we see here in emission relative to the microwave background is that heating kicking in from X-rays. And then at a certain point, we actually start to see UV emission eating away at the actual neutral hydrogen, and eventually this goes to zero. I can't see any more contrast because none of the hydrogen atoms are neutral, and therefore this transition does not exist anymore. So measuring this curve is something that the groups are trying to do. I have not myself tried to do it. I try to limit the number of impossible things I attempt to just a couple, and this seems very hard. So instead, what we're going to try to do is, instead of measuring this average, we're going to look at the fluctuations. And I think what I can maybe even convince you from this picture by itself is that there's some correlation between the fluctuations in the emission as a function of position on the sky or position in a three-dimensional cube, and what else is going on here. And so it's more complicated, but it turns out it's usually easier to measure fluctuations than it is to measure some absolute number in an experiment. I'll skip this slide for too much detail. Okay, so how are we going to measure this? So one of the things that I need to do is not only have a frequency axis so I can measure the dimension I was just showing you, where in frequency is the hydrogen emission coming from, and therefore where in redshift, and therefore distance or time in the universe's history. But I also need to be able to measure spatial variations from point to point. We're doing this at a few hundred megahertz, so we don't have good CCD cameras or anything like that. We have to use radio receivers, and in order to get any sort of resolution at all, we're going to have to use interferometry. So what I'm showing here is an example of a radio interferometer where each of these, I don't know if you can see it from the back, they're parabolas, metallic parabolas. They're actually 14 meters across to give a sense of scale, arranged in a big grid here. And what we're going to do is try to measure the correlations between radio emission arriving at the different antennas and use that to make a measurement of the spatial variation of the material. So let me show you sort of a couple of key things about this. Probably Johnny has given a talk that uses some of these slides in the past, but for those that don't think about this on a regular basis, one way to think about what an interferometer is doing is there's light arriving from some distant source in some direction, and there will be some time delay between when it arrives at two different antennas. Now, if the source was like directly up here, the time delay would be 0, and as the source moves off to the side, the time delay between when it arrives at one antenna and the next. It's just sort of the projected distance between them. And so that's a measurable quantity, and that's the thing we're going to try to measure. And of course, the longer the time delay, the more precise we can determine the position of the object. And so when I think about interferometry, antennas separated by large distances allow me to determine precise variations in angle, and antennas separated by short distances are less accurate, but they will be sensitive to larger angular scales on the sky. So in some sense, you can maybe see where this is going, that I can think of the interferometer as kind of like a Fourier transform device, that modes with high K are measured by distantly spaced antennas, and modes with low K are measured by closer spaced antennas. Okay, and I will probably skip this for the. So one of the things that then happens if you think about, so that's what's happening spatially. And now I want to bring that frequency axis back into things. So if I have two sources that are in different spatial locations, they'll have some time delay in their arrival at the two antennas here. And in general, that will produce a correlation whose peak is well separated in time between these two different sources. But in order to do that measurement, in order to get this time delay, I effectively have to Fourier transform the frequency axis of my measurement. And so there is now a question of, what does the spectrum of the source look like? So if the spectrum of the source is effectively constant, then it comes outside of my integral here, and indeed my correlation is going to peak at a well-defined time delay. The more complicated my source spectrum here is, the more this envelope is going to get convolved with some complicated sort of function. Okay, so there is, in principle, a way to tell where the source is by looking at the time delay, but a complicating factor is what is the shape of the spectrum of the source as a function of frequency. And so the idea here is that most of the sources of emission that emit in the radio at 100 megahertz, where we're interested, turn out to be synchrotron sources. So these are high energy electrons out there in the interstellar or intergalactic medium that are interacting with a magnetic field, and they're spiraling around that field. They tend to produce very smooth continuum radiation, which is mostly of a power law form. And this image, which is taken, I think, at about 400 megahertz, shows something that looks like what you would see if you looked in the optical, which is, here's the plane of the Milky Way, there's the center of the galaxy, and there's a bunch of stars. Except that nothing you're seeing is starlight. So all of the Milky Way emission here is energetic electrons from supernova remnants from exploded stars filing around. And so you're seeing regions where a lot of star formation has recently happened. And every place you see a dot up here is not a star, but rather a supermassive black hole in some distant galaxy that's accreting material and producing lots and lots of energetic radio radiation. So all of these sources are synchrotron sources of one form or another. Some are more energetic than others, but all of them we expect to have relatively smooth power law-like spectra. And so if we compare what we think the foreground sources are going to do to what the hydrogen emission we're interested in is going to do, there's a clear difference. So as I look back through a slab of material here, some of the hydrogen is dense and neutral, so I see a lot of signal from the 21 centimeter transition. Some of it is ionized, so I see none. Some of it is neutral, but not as much of it, and so on. And so I see a constantly fluctuating function here. And so the spectrum that I'm going to see from my hydrogen emission has got a lot of structure in it. And those of you that are good at taking Fourier transforms in your head will notice that this sort of looks like white noise, and so it will be spread out over a range of conjugate variable. Whereas a function like this that's smooth will be relatively compact. So there's a way to tell these two apart. So your question of the microwave background was great. They're using spectral information because they know the microwave background is a black body, and the thing they're looking for, the other things are not. Here we're using the fact that we don't know the details of the foreground spectrum, but we do know that they're spectrally smooth in the sense of their Fourier transform is relatively compact. And the thing we were looking for is definitely not. So we have this way of telling these things apart. So even though the actual signal is enormously bright, it is spectrally smooth, and the thing we're looking for is not. So from a practical point of view, what this means for our observations is, in principle, I would like to reconstruct the image of this fluctuating hydrogen on all spatial scales as a function of frequency. In practice, I'm going to find that there are some spatial scales that are inaccessible to me because of the interaction of the interferometer and the fact that the foreground sources are smooth and bright. And so if I think about, this is supposed to illustrate sort of 2 dimensions of a 3-dimensional Fourier space. The K-modes that I can actually measure fluctuations in are going to be limited fundamentally by the fact that there are bright foregrounds and the interferometer tends to smear them out into this place here. So I will lose all of these modes. My instrument tends to be imperfect in various ways, which will also spread foreground power out. But there's hopefully some range of Ks up here where I can make a clean measurement. And so that has been sort of the hope, is that I don't actually get pretty images like this where I can clearly see, there's a neutral region that's in blue here and an ionized region that's not emitting anything in 0 and black. But if I look at the power spectrum of this, there will be some range of Ks for which I can still measure the fluctuations that are due to the hydrogen and not to other things in the universe. Okay, that was probably the most technical bit of the talk, but I want to be able to connect back to the theory here to the actual measurements. Okay, so the way we're going to try to extract this optical depth here. So I've been talking about fluctuations in the strength of the hydrogen measurements. Somehow I need to be able to relate that back to what is the free electron density as a function of distance away from me or time in the universe or something like that. And so what we're going to need to do is basically build up a model of the hydrogen fluctuations that is based on a model of what the free electron density is doing, and then compare that to the observations. So I think I've given a version of this before. Let me give it in pictures here. So I imagine that as time goes on, the universe goes from being, read this correctly. So we're reading from right to left, unfortunately. This is early times on the right and later times on the left. So the universe is mostly neutral over here. So this is the quantity that is most closely related to what I want to measure, which is actually the spatial average. You know, what fraction of the hydrogen at a given point in the universe's history is ionized, because I can relate this to the electron number density, and that gives me this optical depth, the Thomson scattering. So ideally, I'd like to measure the bottom. The actual thing that's more like what I can measure is the ionization fraction as a function of spatial position, but the real thing I measure is this thing in the middle, which has to do with both the fraction that's ionized, the density of material, and whether it's been heated up or cooled down. So somehow I've got to go from measuring the central thing to kind of back to here and then back to doing the integral in order to get tau. So the way we do this in the computer is you make a simulation, and the computer knows what's the ionized fraction as a function of redshift. You present the actual observable here, we're going to turn into a power spectrum. So I don't see bright spot over there, dim spot over there with my radio interferometer, but I can measure the power spectrum of this. And I can do this in slices that are effectively as function of time or redshift. So at any given redshift, I can go to my instrument, ask what the fluctuation spectrum looks like, and I can do this for both my observable data and for my simulations. And because I have a whole suite of simulations, I can now hope to do the following, which is compare the power spectra that I see with my instrument, fluctuations as a function of time in the universe's history, to my theoretical models. I then take that back to what ionization history corresponded to that theoretical model, and then I can compute the optical depth from that. Now, anybody who does this for a living is now probably screaming at me, how do you know that the theoretical model that you're comparing your data to is correct? If you're a particle physicist, you have the standard model, which is a very good model of what you're going to observe in your experiments, and therefore you can be kind of confident that what you're going to see is, what your simulations tell you. In our case, we have models of how the reionization process is supposed to happen. In detail, of course, these things are going to depend on what galaxies are doing and all sorts of star formation things, but even the simplest models will have a dozen free parameters in them. And every theorist has their own favorite set of free parameters. And so the question is, at some level, how are you going to be able to tell whether or not all of these possible theoretical combinations actually map uniquely onto the thing you want to measure? So what I want to sort of skip through here is we decided to sort of test this out by picking 3 different theorists' models and sort of comparing and contrasting. And the thing that I wanted to get at here, I'll skip through a little bit, is if you go through and you say, let me simulate an observation of the fluctuations, let me simulate trying to recover the parameters of the model from that, and then let me try to work backwards to figuring out what the optical depth is that that particular theoretical model implies, you have some sort of process that looks like this, where I've tried to find the best fit parameters in this high-dimensional space, and then use those parameters to reconstruct what that model says the ionization history, the ionization function of time is, and then go back and reconstruct the optical depth from that. And if you do this for a living, you'll notice that my ability to reconstruct any given parameter here is pretty poor. What is this supposed to look like? It's supposed to look like little ellipses centered on that crosshair. Right, that says when I fit my model, each individual parameter of the model is well determined in my fit. And you can see in this case the spread of possible model values is sort of all smeared out for all of the different internal parameters of this theoretical model. And yet, when I go and ask what optical depth does that imply, this distribution for that one parameter is quite tight, and it's quite close to what I put in theoretically. So I did a simulated observation, tried to work backwards to what it implied about optical depth, and I got the right answer. So there's something sort of strange going on here, which is I didn't actually constrain my theory very well at all, but this one parameter turns out to be pretty well constrained. And more to the point, and so the thing to just look at is that in this far right plot, the reconstructed value, as I change which theory is generating the numerical experiment and which theory is analyzing it. So I take one theory, I generate a numerical experiment, I analyze it with a different theory, which is presumably wrong. What I find is that regardless of that, I'm still able to reconstruct the actual optical depth value quite well, even though the parameters of the theory are not actually being well reconstructed. So what this suggested to us, and I'll skip all of the plots that show this, is that there's something simpler happening here. That there's some simple way in which the optical depth is being reflected in the measurable quantity of the power spectrum. And doing all this Markov chain in Monte Carlo is kind of hiding the fact that there's actually something simpler going on. And so we wanted to try to understand physically, why is it true that it doesn't really matter which model I use or which model I use to analyze and which model to generate the data, I can still sort of get the right answer. And the thing that we realized, and maybe I should try to summarize it a little simpler on a slide, is that what the optical depth really is telling you to first order is when in the history of the universe did we go from being mostly neutral to mostly ionized. And in fact, in the old days, we went back and looked at this, that was exactly the model people used. They said the universe is completely neutral up to some point, and then it becomes completely ionized. And we can calculate an optical depth based on that, because that tells you what the free electron density is from that point forward. And it turns out that all the things you might think would complicate that, like how long it took, and whether the way in which it ionized early was different from the way in which it ionized late, all that seems to matter much, much, much less than when did it happen. And moreover, you might say, well, okay, but you told me you're measuring fluctuations. How do they tell you when anything is happening? And we went back and looked at some very old papers, and people pointed out, if you look at the amplitude of the fluctuations, they're small early on because the hydrogen distribution is smooth. As you get to about 50% ionized, about half of the hydrogen is neutral, half of it's ionized, there's big fluctuations from point to point. The variance goes up. and at later times, when everything is ionized, the variance goes back down. In other words, there's a relatively simple rise and fall in the amplitude of the power spectrum and the variance of the fluctuations as time goes on. And when that happens is very tightly correlated to what the optical depth is. So indeed, after doing all of this work, you discovered that underneath it, there's kind of a simple story. If you think that most of the ionized free electrons that contribute to tau are coming from this ionization process, just watch, see the power spectrum come up and see it come back down. And the details of all of the different star formation processes and so on are kind of second order to just watching that process happen. And so we went through some more analysis to try to figure out when you're looking at the power spectrum, does it matter at what time in the process you look? Is there a particularly important time to look? The answer turns out to be yes, right around the midpoint. You definitely want to get that. But probably more important is to get the fact that it rises up and then falls back down again. And then the other thing we asked was, does it matter whether do I need to look at large scales in the universe? Do I need to look at small scales? Is there some particular way in which the power spectrum is hiding information only in one place versus another? And broadly speaking, what we found was across a wide range of angular scales, if you can see the power spectrum go up and down, that's the thing you need to do. Right, so it isn't like it only shows up if you look at the very largest scales in the universe, or only look at the small scale details. So all of this to say, this is good news for the observational side of things, which I'll try to wrap up with, which is I just need to be able to measure over the time period that I think that the reionization process is happening, which we're going to say is roughly redshift 6 to redshift 10. And I need to be able to see the power spectrum kind of go up and down over that time period, but I don't have to have a very detailed model of the power spectrum. Okay, now this is one parameter, tau. It is intrinsically kind of a summary parameter, so it's not like the microwave background where I really need to see all the bumps and wiggles and have a detailed model of it. It turns out this one might actually be sort of simple, at least if this is the only thing you want to know. And of course, I do have to add the caveat that we're doing all this under some assumption about how well I can do the measurements. And what I'm saying is sort of the current level of the instruments that we're talking about here, the details of the theories aren't that important. If you made a better measurement, I'm sure you would see differences between the theories that you start to be confusing. So we will save that for a future problem. But let's see where we are in terms of being able to do it at all. Okay, so earlier I showed HERA, which is the hydrogen optical reionization array. And this is, from many years ago, Photoshop here. So we took a real picture of the Karoo Desert in South Africa and superimposed a bunch of fake antennas on it. And for many years, this is all we showed. But over the last decade or so, we've put together this entire array. This is now not Photoshop, but a real Google image. So there are about 330 14-meter antennas packed into this hexagon here, and then you may not be able to see well at the back. There's some more scattered out at greater distances to try to get better angular resolution. We've effectively never used those. It's kind of sad, but I'll skip past that. So most of the data I'm going to show you comes from about 200 of these antennas of the total of about 330. And I do like this image because it shows sort of like bacteria growing in a petri dish here, the progress of building the array over time. You can sort of see the hexagon starting to fill out there from the Google images. Over here on the right, by the way, is the South Africans' Meerkat array, which is a low-frequency radio telescope with slightly higher frequencies that they're building as part of the square-kilometer array project. So we've been sharing a site with them for 15 years almost. Okay, so there's the instrument. And it's really high tech. There's chicken wire and PVC pipe and telephone poles and concrete and all the things you expect of a modern experiment. So in order to build a lot of these things, you got to do it kind of find a way to do it relatively cheaply. One thing that wasn't so cheap was at the focus of this parabola, you need to put a receiver that can cover a pretty wide range of frequencies because we're trying to get from redshift of 27 down to redshift of 5. in about a factor of 5 in frequency from 50 to 250 megahertz. And so this engineering marvel is a way of recording radio waves over a pretty wide range in frequencies. We have to amplify them by about a factor of 1 billion. And then all of those things need to be digitized. There's another stage of amplification, digitized and then cross-correlated. So there's sort of a small supercomputer running out there in the South African desert doing all of this for us. We've experimented with what kind of thing we put at the focus of our parabola over the years. So the initial results that have been out for many years now came from a relatively smaller bandwidth, smaller range of redshifts, and a funny looking thing that looks like a cylinder. And then this is our new, more advanced receiver. Okay, and initially we had just 2 bands here. You can think of them as roughly redshifts of 8 and redshifts of 10. And one of the important things that came out of the early limits from Hera, this has now been out for 4 years or so, was that the early universe at redshifts of 10 or so had to be kind of warm. And that turns out to be kind of a technically important thing. It definitely makes my life easier from the point of view of measuring tau, because once the hydrogen gets warm enough, that is to say, once it's significantly warmer than the microwave background temperature, it ceases to be important in the equations. And so it kind of marginalizes itself out of the problem. So if we can be reasonably confident that the gas is warm by redshifts of 10 when we think the reionization process starts, it's one less parameter we have to worry about. And my picture that I gave you of watch the power spectrum rise and fall becomes even more accurate. So we think that that's actually true based on actual data. And this is sort of a plot only a mother could love, but I want to just point out that the initial results we got from the experiment were only in 2 redshift bends. So we covered a relatively narrow range of time in the universe's history. And all the different panels here are different places on the sky where you're looking, because they all should have given consistent results. So you look in different places, you should get the same answer. You don't quite. And the other thing I want to point out is you can see the effect of not being able to completely get rid of all of that foreground emission as these points down here at low K. So primarily, the points that are contaminated with foreground emission are the ones at lowest K. However, unfortunately, that is also the point at which our sensitivity is best. So the noise curve here is in black. And so we would like to be measuring at the lowest possible Ks. That's where our instrument is most sensitive, and that is, unfortunately, where the foreground is strongest. So that's the thing to sort of take away from this without going into great detail. And this was my summary plot that said we did a bunch of analysis and convinced ourselves that the hydrogen at redshifts of 10 needed to be reasonably warm, warmer than the microwave background. That was the key science result. And I'll come back to this plot. In the next phase, so this was the initial result was a relatively restricted range of redshifts and a relatively small number of antennas. We were able to increase the number of antennas dramatically, and we had this wider redshift coverage. And so we have now got, so the results I'm going to show you, we have about 70 times more data in CAN than what I will show you, so that's why you should be hopeful. I'll also show you why we may still get stymied. We've primarily focused on a relatively small patch of sky. It turns out, for those that are looking for an interesting challenge, that patch of sky overlaps with the microwave background experiments from Simons Observatory, and so there's an interesting question of whether we could ever get anything from cross-correlating with CMB data, but so far the answer seems really hard, but I thought I would point that out. So the current results, which are now out, in fact, I got the email this morning that they're published, but they've been on the archive for a little while, now extend Hera's limits to 8 different redshift bins, and you'll notice it goes all the way from redshift 24 then to redshifts of 5.6. So in context, this is before we think hydrogen reionization started to about the time we know that it was completely finished. All right, so we've now covered a much wider swath of the universe's history. We are only looking at one particular patch on the sky, so we haven't done quite as detailed cross-checks there. The other thing to notice is that the points here are more or less following this noise curve. So we have not detected anything yet, but we are instrument noise limited. So we are actually hitting our sensitivity threshold as we had hoped, except at the very lowest Ks. So I'm going to point out the dirty laundry, which otherwise would not be visible in such a busy plot. But here, the curve in sort of a darkish purple is the older result, okay, which is, sort of comparable in amplitude. But at the very lowest Ks, it is better than what we're actually measuring. And so we think we have accidentally kind of done a bad thing by going to these new feeds, that the antennas can now talk to each other electromagnetically in ways that they couldn't before, which is not what you want. So where are we, and where can we hope to get over in the next few years? So if you assume that we can't do any better with this problem at low Ks, if you assume that we have to cut roughly the same fraction of data from our 4 years of data that we have in the canon that we have had from the first few months, yada, yada. So relatively conservative assumptions, we can hope to move down our limits down to here, and we're trying to get down to here. So that doesn't look super promising. Although I do remember many years ago being in a LIGO talk and looking at 4 orders of magnitude and strain that they needed to come down, and they did manage to pull off. So this is a relatively conservative thing, but I think we are within shooting distance. In the interest of, the other thing is that this is sort of stretched out linearly, the redshift range. We really, for measuring tau, only care about down here. And there, I think we're within a factor of a few of actually being able to make the detection with the data that we have in hand. It will require improved analysis techniques, but we have not tried out most of the things that we have in mind for these limits. So there is some hope that the analysis will also get better in addition to the straight up sensitivity. Okay, so I will just conclude by saying there's still a ways to go. But if we are able to reach the sensitivity that we think we can, just based on the sheer number of antennas and integration time and so on like that, our error bar on this quantity that we'd like to measure becomes better than the current state of the art with, in principle, a year's worth of observations. So it's worth making the attempt. And it's also worth pointing out that with other methods of determining the optical depth from the microwave background itself, of course, they are jointly fit with other things. Whereas here we are bringing an entirely separate way of measuring this quantity into the picture, which doesn't depend on any real assumptions about the microwave background or anything else. We care about cosmological parameters, but we don't care about anybody else's measurements of the microwave background. And we should be able to do as much as a factor of 2 better than the current limits if we can pull this off. So, like I said, I think it's worth worth making the attempt. For those that really want to talk about instrumentation, I will do that, but I will put my conclusions there, which is we made considerable limits in placing limits on the power spectrum itself. We have the ability to do better in the future. The tau constraints don't seem to depend heavily on the theory that you use, which is good. And we just need to be able to make the detection at all. Right, I will make my shameless promotion here. So I recently wrote a book, and it's published. And if you're interested in teaching sort of major level astrophysics using Python and interactive techniques in the classroom, I would love to talk to you, and I would love you to take a look at my book. It's free if your library subscribes to the IOP Astronomy, which it very likely does. So I don't get any royalties, but take a look and see if it's useful to you. I have other resources available for it if it strikes your fancy at all. So, thank you very much.
Got time for some questions if you want to self-manage. You can call on people if you prefer.
Sure.
So previously when you were saying the mod, it's kind of model independent, this tau. Is there a way to think about it in terms of this is just some kind of phase transition and like everything is maybe somewhat scale invariant? So in the sense that, well, just like the peak is exactly at the transition point, which are exactly in a phase transition where fluctuations are largest. And if we're talking about scale invariant phenomena, then you kind of just have a Landau type theory where the details of the model doesn't really matter.
That is a really interesting. So the question is, can we think about this? The fact that this is more or less theory independent is because this is a phase transition. So
Correct.
I'm actually, it's a great condensed matter question. I can never keep my phase transition straight. we've often in the past said this is a phase transition in the universe, but I don't know how seriously we've meant that in terms of like analyzing it from
I mean, just like
true line theory.
practically speaking, it's just, okay, let me just look at the k dependence of the fluctuations. Is it more or less some kind of scale invariant? Like the correlations are more or less just scale invariant in general.
That seems to be broadly true. So when we looked at the sort of Fisher matrix analysis, there's information about this transition at all scales that we measured in the problem. And I think that is an interesting insight, because one of the things that I'd worried about some years ago was, does it matter whether the bubbles form in sort of, they're very spherical, or whether they're much more diffuse or something like that. And if you're right, it would suggest that it really doesn't matter. That the information is sort of independent of exactly how the bubbles form, which would be nice to be able to show. Yeah, I'm not sure I can give a better answer off the top of my head than that, but I think that may be the gist of it.
Yeah.
And in some sense, the power spectrum is much less sensitive than if you would look at the detail.
I mean, it's very
morphology.
suggestive. If there's scale invariance and it's a phase transition, there might be some effective theory that just says, there's some scale invariant model that does a good job, and all the models just converge to that point.
Right.
Yeah.
Yes.
Could you elaborate a bit further about why it might be a bit difficult than initially anticipated to cross-correlate with like the Simons Observatory?
Okay, so great. I can pontificate a little bit. So there's a couple of different ways to get tau information from the CMB. Simons Observatory is not going to get to large enough angular scales. Well, we are not forecasting we will get large enough angular scales to do the EE bump, which would be the sort of easiest thing to do. So in fact, what we're going to attempt is to look on small angular scales. You look at the fact that the KSZ effect is patchy because some of the light passes through an ionized region and some of it passes through a neutral region, and the ionized region has a peculiar velocity. So that will cause a KSZ shift. So the first thing to notice about that is you could imagine doing cross correlation there, because now you're looking at a patch of sky and you say there's some KSZ from a ionized bubble that's moving, and there should also be a hole in my radio map at that spot. Except that because the KSZ is both positive and negative, the shift on average will cancel out if you have to average over many regions. So what that immediately pushes you towards is at least a 3-point function where you have to think like the square of the KSZ field times the 21 centimeter one. So we did write a paper about this. In principle, there's a detectable signal. It is not so easy to interpret, but it does show an interesting sort of change in sign at about the midpoint of reionization. So it's like, but the other problem that we noticed about it is that level, the 3-point correlation effectively requires you to measure the 21 centimeter inside that foreground exclusion wedge. And so you have to do some sort of magic with getting rid of foregrounds in order to make it work. If you go to a higher point function, you can do it, but now in general your signal tends to decrease as the number of points in your correlation function, so that becomes a harder thing to do as well. There have been a couple of recent papers that have looked at whether you can cross-correlate with CMB lensing, which is not a thing that I had thought about. So the CMB lensing kernel is quite broad. That's to say, you might say, the CMB is at redshift of 1100 in the very, very beginning, and now you're talking about asking about what lensing happens at redshift 10 or something, but it turns out that there is some contribution to CMB lensing from stuff during reionization. So there have been some interesting suggestions. I think Chime is actually thinking about doing this at lower redshift, cross-correlating CMB lensing with 21 centimeter. You might be able to do this at higher redshift. So there may be a different way of doing cross-correlations that don't rely on the KSZ effect. My current thinking is the thing we should definitely spend more time thinking about is just a joint, internally consistent prediction for KSZ 2 and 4 point combined with 21 centimeter from a common theory, so they're mutually consistent, and then trying to get a joint likelihood that way. That should be the sort of like the zero order baseline, but the cross correlation stuff might work. They're great questions.
Is there any way measurements of tau can help restrict sterile neutrino models?
Okay, the question is, I guess strictly speaking, you're asking, can some of the neutrino mass measurements tell us anything about sterile neutrinos? And then, of course, measuring tau would help with that. I think so long as the sterile neutrino has mass, it will affect the matter power spectrum, which is the basis of the CMB measurement, basically looking at what happens to how matter is clumping up as the universe evolves. And I don't think the limits are terrific, but there are currently limits on how much mass you can have in a neutrino-like species already, right? And so then presumably you would get the sum of all possible neutrino-like masses in your constraint. But I haven't really thought whether you can do anything. You have to know more particle physics than I do to say whether you could separate out the fact that it's sterile from three generations we know are there.
Maybe one more question.
So you haven't mentioned the sort of edges type result. Is there a way of getting at the epoch of reionization, since it seems to be sensitive to the midpoint through a total power measurement?
Okay, so the question is about an experiment called EDGES that it was not measuring fluctuations, but was trying to measure the total radial emission as a function of frequency or redshift, or however you like to think about that. And they reported a detection of a very relatively strong signal at redshift of 17. And so far, no one has been able to reproduce that result. And unfortunately, it's not terrifically easy. So here's the sort of standard picture of where things should be. And important in this picture is both the breadth and the depth of this feature that we do expect in absorption. So this is sort of a standard, let's form stars, X-ray binaries around black holes, and then start to heat up the IgM from X-rays and increase star formation. And so indeed, one does expect a dip at roughly the same redshifts or frequencies here, but it's broader and importantly shallower, by like a factor of 5 than what is reported. So it's been a real question how you explain a relatively sharp, in the sense of the evolution of the universe, and relatively deep dip like this, because this is actually saying the hydrogen gets colder than the microwave background in sort of the simplest interpretation. So how would you do that? So there's been a lot of theoretical suggestions for how you might do that. Unfortunately, the problem is without a good theoretical suggestion for how you do it, it's hard to predict what the fluctuations amplitude looks like, right? So the monopole and the fluctuations are not so tightly bound to each other. So I think Hera eventually could say something about whether there could be a trough this deep at redshift 17, but it's actually not as easy as you might have hoped.
Sorry, if I can continue. I wasn't just thinking of edges itself, but an edges-like thing.
Right.
Because effectively, when you're saying that you're sensitive to sort of this flip, you're sort of making an edges-like, this is how much, when is the transition actually happening overall argument. And so
right.
Even at redshift 7, you'll be able to see, the argument is you'd be able to see that sort of equivalent total dip at a different redshift.
Right. Okay, so the problem there, I think, is that roughly speaking, in a model like this, the 50% ionization point is happening sort of over here. And so the actual global spectrum is quite smooth. What the global spectrum people have sort of made their hay on is saying, well, we're looking at this in the presence of some very strong power law foreground whose detailed shape we don't necessarily know, but we can look for places effectively where the derivative in the signal changes time, where it changes sign, where there are inflection points. And the problem is reionization is sort of the least interesting in the global signal because there's no inflection point. It should just be an overall decline. So you really have to do a good absolute measurement in order to do it. That's why, I mean, even the KSE cross correlation was kind of exciting because it showed a sort of spike at the midpoint. And with the power frequency, we sort of see this rise here. It's very featureless. So it's possible, but I think hard.
Well, let's thank James again.
Step out of the room within a couple of minutes, but questions from other folks out in the hall or in front of the door.
Was that? Oh, pretty good. Oh, yeah. Sort of, are we actually converging on anything?
Yeah, because what I was noticing is that for 2025,
as long as they're
Because it's the lowest K where it should be better.
But no one really cares
is
about
contaminated before.
In principle, they'd be
So basically, it's the fact that the purple point here is slightly above the dark purple point, and it's also above it here. That we're actually slightly
definitely less faculty.
worse.
I think just timing.
Like where is the best one? Because the other thing that we're doing here is, so I didn't have time to really explain. Yeah, so we had the feed in the here. So the new feed seems to have this leakage problem. Very otherwise,
Yeah, but I mean, if you have data,
the good story is we got every other K got the same limit 10 times more stock.
statistics on how
But the one that actually makes the money is
much interesting, very different.
Is there like a super simple? You guys are just
Oh no, I think
I just have a quick question about that last
The reference that I always think of, the simplest one is Cardar.
kind of
I wouldn't say
no,
that's
the one that we were just looking about.
Oh, the edge.
Yeah, but like, it's like statistical
And
mechanics.
this is just because well,
Oh, yeah.
I'm trying to. I want to be as concise with
I
you.
mean, the basic idea is just that.
Why
Year of
are we?
transition.
Why are you so quick to think that we're not in a reflection point right now?
okay.
And we're not viewing this where we are now about to go back up, and then it's going to.
It really is actually good.
in a cycle.
Just generally
Oh
characterized.
well, this is sort of everything here has already happened.
Yeah. So the reason I say that is because this is a measurement of cosmic time, right?
Yeah.
And I don't know much about this stuff in general, but if I'm just looking at a pattern here, right? If you look at brightness and your negative, whatever, and it goes down and then back up,
So I
and then
think
to the
the
heating
idea
begins.
of,
Then I
like,
start
this,
thinking
like,
about like things I learned in first grade about how you when you heat things up, like from when it goes from a liquid to a gas, right? You don't change the temperature, and you just use the energy for chemical bonds, right? Stuff that, and then after that, you can start heating up, and then you enter this phase, a new phase, which would be a new quote-unquote state of matter. But we're not dealing about that right now. We're dealing about brightness and energy. And so once we're above this, I guess, neutral point of zero, then that's when re-ionization begins.
So it's not quite, because the 0 point here is measuring whether or not the emission of radio waves from hydrogen is greater than the sort of background radiation that already exists.
Yeah, so it's
or
just
whether
kind of
it's
like, in
fainter.
certain cases, just like I have no idea what the
And
theory is.
so
Let me just do some data analysis.
There's
on
more than one way to be
point
zero.
correlation
So
and
one way to
see
be zero is all the hydrogen atoms are in equilibrium
and you see
with
some
the background
normal
radiation.
behavior,
Yeah.
And then I wouldn't see any net
matter,
emission.
just like,
Which is
this
not something we
universal?
care about,
Just do a
right?
bunch of different systems.
And we don't think it's happening.
Which would happen there, right?
Well, it's actually what happens here all back at 0.
So then what is this?
I mean, just
So this
I think we're just
is
biased because of
it has started to warm up again, but of course it
also
hasn't
in
quite gotten
RG
back to
that
0.
this
Yeah.
means that there's something.
Until
But the way to get to
variance,
0
something-
here
there's something
is
hidden
to
that's
erase
everything,
all of the
all the
hydrogen
theories just
completely.
look
which
the
is
same.
not which means that like it's basically usable hydrogen. It's not.
Well,
I mean,
it's
I'm happy to
free electrons and
talk
protons.
about it. I know
So
nothing
we
about
do know
reionization except
that-
for what I just.
So the present time actually would be way over here.
Yeah.
But the thing we know is for all of this time, there basically has to be free electrons and protons only, because otherwise we would see too much absorption from
Also,
neutral
like, there's
hydrogen.
a very easy check. So, like, if you
So
think
if
it's
the universe had
percolation, you
stayed
just
with
go
the hydrogen being
look at the
neutral,
textbook and you say,
then we would
here
see
are the
very
good
strong
points, what is
absorption of
percolation?
ultraviolet
Look at
light.
data,
I'm just thinking of it, but we don't see that.
And we
calculate the
see
critical exponent.
infrared
If they
instead.
match- If they match
Well, we see
exactly,
that
it's
there's
safe for sure that
occasionally
this is a
little bits of
percolation
absorption,
phase.
little
But
pockets of
we say
hydrogen
The term is
absorbing
the
light as it comes
universality
along.
class of percolation.
Ultraviolet light.
Yeah.
But basically the
But that's
UV
actually
light
like a
is,
very,
the universe
very
is
quick
basically
check to
transparent.
have the
which it wouldn't be if it were filled with neutral hydrogen.
That's actually that's really interesting. Do you think that, like, really quick, do you think that there's some sort of importance of thinking about time and less of a classical way of thinking about it, and thinking about it as more like from the light's perspective that's been traveling, that we can only see 5% of, from the fact that we're seeing it, so it's even less than 5%, right?
Well, we're seeing 95% of the background.
Well, we're seeing 95, and the 5% that's absorbed before.
Yeah, or scattered into some.
And so, out of that, like, we kind of selfishly take our perspective of how light is traveling through time to create this map, and if we take it through like the evolvement of energy as light progresses through time, which is essentially simultaneous, right? If it's not experiencing time but distance instead, right? If you think about how this graph would change, it would be extremely interesting, because it's like energy obviously seems dependent on time right here, but if it was dependent on something different, like how many things it interacts with, or density of energy in space, right? Which is obviously a function of time, at least we think it is. But if you graph it differently, you get a different shape and a different trend.
But this is just a very specific. So the plot here is not sort of everything. It's like just making a model of what hydrogen atoms are doing.
Okay.
Right. At a particular wavelength. Right. So it's not even all of the interactions with hydrogen are even included in this plot.
It's just the time.
It's just the interaction with radio waves versus.
Okay.
Yeah, well,
I think
time from our point of view.
All right, thank you. Hi. I do a lot of work with 21cm fast and 21cm
Yes.
Can you tell me about what you were doing?
Yes. So
I want to be on a place where I can write.
So I am not sure that we did we made a lot of use of 21cm MU whenever we could, because in order to get a fast likelihood, you don't want to be running 21cm.
Yeah.
So 21cm MU is reasonably fast.
I read the paper on it like a year ago. I need to refresh myself a little bit about it.
But it's basically they trained an emulator on a big suite of 21cm fast simulations, and so if you drop in their fiducial mining parameters, you get out a power spectrum as a function of redshift, the optical depth, the ionization history. I think they give you a bunch of UV luminosity functions as well. So that was a piece of information we weren't actually making use of, but they'll give it to you. And so you can basically skip over the step of simulating the full data cubes and just get the process products for that set of parameters.
When you were inputting like Z-re-ion though, light cones, what were you doing?
Yeah, so Z-re-ion is this thing with heat track and Nick Battaglia and Paul LaPlante. You start with a density field. So we actually simulated that using 21cm fast. And then you do this thing where you apply a Fourier space bias, and then you use the resulting thing to tell you at which redshift any given point in the cube ionized. That gives you your ionization field. So you have an ionization field, a density field, and then you have your twins, and it ignores the spin temperature.
Yeah.
And then you have your overall scaling factor and determinants in your brightness. So you can multiply those things together and basically get a data cube. And it is fast enough that I think we didn't even bother to build an emulator. We just ran Z-re-ion for a set of, but the input parameters are not physical. They're basically what's the slope and amplitude of the bias and what is the midpoint of reionization.
That's an input parameter.
And so I think we ended up with, the fiducial is 3, but we ended up making B0 a free parameter because we found that we couldn't fit all possible 21cm fast things without letting the amplitude float.
So I guess my concern was, so you're not inputting like Z-re-ion light cones into 21cm 21cm MU, right? Or
so
like,
sorry, I went through this too fast. But one of the things we did do was we generated 21cm fast. So some simulation using 21cm fast and going over to the power spectrum. And then we said, let me analyze those power spectra with a likelihood where the model power spectra are generated by Z-re-ion. So I'm actually analyzing it with the wrong model.
So you basically have 21cm MC running Z-re-ion
power spectra
I
fitting.
think we wrote our own MCMC sampler.
Same idea.
Yeah, exactly. But basically, instead of using a likelihood based on 21 CMFAS, we wrote a likelihood based on Z-re-ion and on micro 21 CM.
I don't know the input parameters for Z-re-ion, but I'm guessing that you gave it like a minimum and maximum redshift or something. When you ran 21 CMMC or your own MCMC, were you matching for like the minimum and maximum redshift of the box, or were you matching like by ionization fraction or something?
We started effectively with 21 CMFAS as our sort of baseline and said I'm only going to consider 21 CMFAS simulations where T-spin is well above TCMB at redshift of 10. So that was a first criterion. So we threw out all the models that didn't have that. And then I think we picked, apart from the T-spin parameter, we picked sort of uniform coverage in each of the, basically the same thing that Daniela did for the emulator. We picked some range of the 21 CMFAS parameters that sort of the likelihood has to stay within these bounds.
Yeah.
The idea being the emulator isn't going to give you a good answer outside of those bounds anyway, so you might as well impose that as a prior.
Yeah.
But I think I said, I think the only one we explicitly restricted otherwise was the spin temperature. And the reason was that Z-re-ion it already assumes the spin temperature is high. So we couldn't compare apples to apples at all if we had the spin temperature in the mix. And then I think with Z-re-ion, let's go back and look at the paper draft. We had some set of bounds on, but that basically said that the reionization midpoint had to be between 10 and 6 or something like that because we weren't allowing anything else. And I forget K0 and B0 we had to say were within some reasonable range of K0 is the pivot point for the bias in Z-re-ion and then the overall amplitude. But I can look that up for you. I mean, it's a little bit arbitrary, but it was sort of designed to cover all of it. We basically found that, so Z-re-ion is interesting. You can get very unphysical ionization histories out of Z-re-ion. You can effectively get almost instantaneous reionization with some combinations of parameters. And there's a huge degeneracy between, I want to say like K0 and alpha. It's the classic problem with the power law that you can change the pivot point if you also change the index, and they will look very similar over a narrow range in K. And so there was some big degeneracy that we had to like exclude some part of the parameter space just to avoid it spending a bunch of time in a degenerate region. Yeah, I'm not sure if this is helping.
Yeah, I was specifically concerned about, and you did answer this, like what you were doing when you were like, you had said you were like assuming like a Z-re-ion like power spectra when you were like inputting 21 CMFAS data. I was concerned about that specifically. Do you know when the paper is going to be uploaded to the archive? I would love to read it.
Yeah, I've been trying to finish. I had the student unfortunately defended their thesis in May and has gone on other things, and so I'm trying to both get a little bit of their time back and also put in some around to try to finish it off. So I would like to, not anytime soon. It'll probably be early summer.
Okay.
It's going to take me another 3 months or something to
Yeah.
go back and reproduce some of this stuff that to my own satisfaction. I've gotten burned before about just trusting that a student
Yes, no, I
did everything correctly and just sort of putting their plots in, and so I wanted to make sure I could reproduce. The other thing I wanted to check, because one question that I have been asked when I give this talk is, obviously if you don't make any detection at all, you can't say anything about tau. So right now we have no constraints on tau from HERA, but how deep do you have to get before you actually could? And so we have done things where we've sort of put in some 21 CM sense forecast, and that works. But then if you backed off that, I don't actually know where it falls apart.
I mean, my
And the
hunch
other-
is getting the rise is the hardest part.
I think
Seeing it falling, the noise is dropping faster than the power spectrum.
Right.
But similarly, the noise is blowing up at high redshift faster than the rise.
And so we put a lot of effort into just making a Fisher matrix for tau only that was reasonably simple to evaluate. And then I realized that General sort of didn't give me an easy way to evaluate this thing, so I could try it with different noise levels as a function of redshift and K, which is the obvious thing to do. It's just ask, where's the crucial thing? Because I think you're right. I think once we realize that it's the rise and fall, it's sort of like, if you can't measure the highest redshifts well enough to distinguish them from noise, then you're just going to see a fall.
Yeah, I think I cooked up some toy models once where I said you could get a 10 sigma detection of the power spectrum and not see the rise and fall.
Yeah, and that would be, we would only get the constraint that tau has to be. You might get a lower limit, right? Because if you say the rise has to be somewhere higher than what I measured, but you would not get the actual measure. And of course, the other thing is that if you had to include T-spin in this, then I think my picture gets much more complicated. Because the spin temperature can have the effect, depending on the timing, of just sort of, again, making it just look like there isn't a rise and fall, it's just a fall. So, at least over the range that you're measuring.
Hello.
Thank you. All right. But yeah, so August has been doing work testing model dependence in 21C and MMC. Basically with two different variants of 21C and fast. Because as soon as we started thinking about some z-re-ion, in your plots, you don't get the red crosshairs. It doesn't have a red value for LX.
Right. Right.
Who knows if it's right or not? But as you said, you can maybe do some summary statistics and see if it's the right summary.
Yeah. So that was the thing. Is that, like, I don't even know if I think the thing we noticed is not only is there not the right value for the get, it doesn't even get it to the world line.
Yeah.
If we take from that as well.
But yeah, so I think your day is
Sure. I don't think I got actually a fairly lot of things that I have to turn over today, or an hour out ago.
all right. Okay, we probably have 2 hours.
But if you're free, I'm happy to give you less of it.
it's like the opposite of how things. But I'm still going to take it because I need to understand things. Really think that like when you observe me, I'm there and I'm also there, and you think that's complicated. Why don't you like stop thinking like a circle, be the sphere you want, right? It's like I'm not light, but like to a certain extent, I'm bounded by light and gravity. That's just the truth. And so like, and it's almost a spiritual way of it's like magnetic science. It's like if I decide to want to explore all that stuff, which you probably don't want to, which you can't change either. But like at the end of the day, if I decide to do that, you think that you serve like the man that type of thing. Because it has nothing to do with humans. There's no monetary value to it. It really is nothing to do. But at the end of the day, it has everything else, right? Like most of our universe is space. And so doesn't space deserve things for the necessities, not human existence? It's not philosophy. It's honestly not philosophy. I think it's a pretty standard question. What we stop being so obsessed with how we understand why don't we just accept that in this moment our consciousness is not let's just like understand really look at it at different points of time. And then we get there. But like I'm gonna be honest, you know, the first professors that I actually like listen to. And like I felt mostly crazy when I tried it. But like it's really nice to actually what do you are you a teacher? Do you enjoy it? Just because it's like understanding stuff. I mean, I think enjoy doing things that at least have a constant perspective on it. Yeah, and I have so much. But like, are you taking any students? What about what I have to do? I'm also like open to it. I already learned this stuff throughout the class. I'm open to reading what I can do. Yeah, I mean, honestly, I'm talking to take some data learn about them. The technical skill there is too. Like having like really competition stuff. Yeah, I think that for me, like just really quick, I think for math, it's a little bit weird because math is very, it's similar to understanding computation. At least like I think that it has its beauties and senses, which pretty much means it has its like literally dramatic correction. It happens like almost all the time. And I think that like when I see math, it's really not like a bunch of these symbols, it can be scary, but at the same time, it's like I think that I have good capability of understanding math without being intimidated by it, which is a little different from Ricardo's but what I know you're probably PhD students, what I think in the future of the what I could offer which is very different is like being part of a project where it's just about learning. Like because like what I'm good at is like writing songs and like